All right, gentlemen, good morning. Today is Tuesday, March the 31st, and today we are going to talk about energy in collisions. We talked about the law of conservation of momentum. We talked about the law of conservation of energy. But interestingly enough, energy, although momentum is conserved in all sorts of interactions, no matter what happens before and after an interaction, the momentum is conserved. Energy is not necessarily conserved because very often it is lost in the form of heat. So let's talk about how this might work. All right. First, uh, a collision in which the colliding objects stick together and then move with a common final velocity, in other words, they move together, is a perfectly inelastic collision. They don't bounce. There's no bouncing. They stick. Okay. A collision, and we know that momentum is conserved in a perfectly inelastic collision. A collision in which mechanical energy is conserved is called a perfectly elastic collision. Okay. Now we know that momentum is conserved here, and now energy is conserved here. All right. Um, so while the momentum is conserved in all collisions, mechanical energy is only conserved in a perfectly elastic collision when the two bounce off of one another. In an inelastic collision, because the two objects are sticking together, some of the energy, especially the kinetic energy, is converted to heat. So let's look at a couple of examples here. All right, first, in example 10.15, energy transformations in a perfectly inelastic collision. The figure here shows two train cars that move toward each other, collide, and couple together. In example 9.8, we use conservation of momentum to find the final velocity shown in the figure from the given initial velocity. So we've already done that part of the problem. But what we're wondering now is how much thermal energy is created in this collision. So let's have a look. We've got two boxcars here. One with a mass of 20,000 kilograms moving at 1.5 meters per second to the right. The other with a mass of 40,000 kilograms moving at negative 1.1 meters per second to the left. When they collide, we calculated that because their masses are together here, their new velocity after the collision by the law of conservation of momentum is negative 0.25 meters per second. Now, what does that tell us about the energy? Well, in this particular case, because the track is horizontal and we're going to use two cars as our system, there's no change in the potential energy, right? We're moving on a level track, right? We're not going down a hill or that sort of thing. So therefore, the law of conservation of energy is that the final energy plus whatever energy is lost as heat, so the delta ETH bit is equal to the initial kinetic energy. And so therefore, because we're still using the law of conservation of energy here, we can calculate the value of delta TH, okay? So the initial kinetic energy, we calculate by calculating the kinetic energies of each of the two cars. So 1/2 m times v1 I squared gives us 1/2 times 20,000 times 1.5, 1/2 times the mass, or 40,000, times negative 1.1 meters per second squared gives me an initial kinetic energy of 47,000 joules, or 47 kilojoules. Now, because the cars are sticking together, the final kinetic energy is 1/2 times the sum of the two masses times that final velocity squared. Remember, we calculated the final velocity in the chapter on the conservation of momentum. And if you do the math here, you get 1/2 times 60,000 kilograms times negative 1/4, and that leaves me with only 1,900 joules of kinetic energy at the end. So obviously, the energy the total energy is conserved, but the kinetic energy, the mechanical energy, is not conserved. We've lost almost 50,000 joules worth of energy here as heat. Okay, so from the conservation of energy equation, we know that about 96% of the initial kinetic energy is transformed into heat. All right, and this is a fairly realistic estimate. Now, in an elastic collision, on the other hand, now we're obeying not only the law of conservation of momentum, but also the law of conservation of mechanical energy. In other words, the total kinetic energy before is going to equal the total kinetic energy afterwards. So we've got two objects. One strikes the other. Here's the during, and then at the after, we know that each of the objects is going to have some final velocity. Now, we don't know what those two final velocities are, but we'll draw the vectors in just as a, so that we have a number here. So by the law of conservation of momentum, in this case, m1 v1 initial is equal to m1 v1 final plus m2 v2 final, whatever the final momenta of both of these. The reason there's not a momentum for the second ball on the left side of the equation is because in this case, v is equal to 0. Now, in terms of the energy, the kinetic energy of the first ball is 1/2 m1 v1 squared. And afterwards, the final velocity, or the final kinetic energy rather, is 1/2 m1 v1 squared plus 1/2 m2 v2 squared. So here, let's try example 10.16. On an air hockey table, a moving puck traveling to the right at 2.3 meters per second makes a head-on collision with an identical puck which is at rest. What's the final velocity of each puck? All right, so we draw ourselves a diagram. We've got the puck number 1 moving at 2.3 meters per second. Puck number 2 is just hanging out at rest. And afterwards, we want to know what the final velocities are for both of these. Okay, so there's the before and after visual overview. Now, the one thing that we have working to our advantage in this case is that both of the pucks are identical in size, shape, and everything else, and so therefore their masses are equal. And so, with a little bit of magical algebra, we can rearrange, because m1 and m2 are equal to one another, we can rearrange the equation to solve for v1f as m1, I didn't even touch the mouse that time, m minus m over m plus m times the initial velocity of the first puck. And of course, because the two values of m are equal, the numerator here is going to give me 0, and so puck number 1 stops after the collision. For v2, now we've got a value of 2m over 2m, so 1 times v1 initial, and therefore the final velocity of the second puck is equal to the initial velocity of the first puck, 2.3 meters per second. So the incoming puck stops dead, and the initial stationary puck goes off with the same velocity that the incoming one had. Okay. On a practical note, okay, this example is kind of cool. Example 10.7, protecting your head. A bicycle helmet is basically a shell of hard, crushable foam, and it's tested by being strapped into a 5-kilogram head form and dropped from a height of 2 meters onto a hard anvil. We want to know what force is encountered by the head form if the styrofoam in the helmet is crushed by 3 centimeters. All right, here we can use the work energy equation to calculate that amount of force. We'll choose the system to be the head, and the earth, and we'll move on from there. So here's our diagram. Here's the helmet on the head of this thing. the head form is dropped from a height of 2 meters. And when it strikes the ground, the styrofoam is pushing the head back up. So therefore, there's a large force acting on the head at this point. So before the height above the ground is 2 meters, the initial velocity is 0, right? Before we drop it, it's 0. At the end, the displacement is 0, and the final velocity is also 0. What that tells me is that the kinetic energy before and after is not going to play a role in this calculation. We're only going to be really working on looking at the gravitational potential energy in this case. All right, because the helmet is supposed to stop your head. So in other words, the final gravitational potential energy minus the initial gravitational potential energy is going to equal the amount of work done by the helmet, okay? And so if we take this and set W equal to the opposite, that's supposed to be a negative sign, of FD, all right, we can then rearrange this equation to calculate the value of that force. So force here is equal to the opposite of the final potential energy minus the initial potential energy divided by d, or if I distribute the negative sign, it's the initial potential energy minus the final potential energy over the value of d. Now I can plug and chug. Because the final potential energy is 0, right? Go back here. So this term, damn it, this term cancels out. The formula is going to be just this, which is m times g times delta y, is 5 times 9.8 times 2 divided by the distance, and this is the distance that the foam crushes, 3 centimeters, and that gives me a force of 3,300 newtons. Now, so this is the answer to the question that we were asked: what force is being supplied here? But just as a little piece of trivia that you can take to your next cocktail party, if we calculate the value of the acceleration experienced by the head, it's 3,300 newtons divided by 5 kilograms, and that gives me an acceleration of 660 meters per second squared. That's about 67 times the acceleration of gravity. Now, that sounds like a lot, right? Doesn't it? But in reality, it turns out that your noggin, your brain, can withstand an acceleration of about 300 times the acceleration of gravity, so almost 3,000 meters per second squared. And so this helmet would do a pretty good job in most bicycle accidents, all right? Nothing exceptionally serious, but in most accidents. Okay, that brings me to the end of section 10.7. Your homework for tonight is to do questions 41 through 44 at the end of chapter 10, odd numbers only, as always. Gentlemen, may the force be with you.